Find the depth of water in feet. In this problem, a rectangular channel with a known base width flows at a constant rate. The slope and roughness of the channel are also provided. Keep in mind, this diagram is not necessarily drawn to scale. Manning's equation for open channel flow in English units is the flow rate in cubic feet per second equals 1.49 divided by the roughness coefficient times the cross-sectional area in feet squared times the hydraulic radius in feet raised to the 2/3 power times the slope as a decimal raised to the 1/2 power. The problem statement provides the flow rate, the roughness coefficient, and the slope. Currently, we do not know the area or hydraulic radius because they both depend on the unknown depth, d. The area equals the base width, b, times the depth, d. And the hydraulic radius equals the area of the channel divided by the wetted perimeter, or rather, b times d divided by the quantity b plus 2 times d. Returning to Manning's equation, we'll isolate the area and hydraulic radius terms, which are now on the left side of the equation. Solving for the right-hand side of the equation, the given values for flow rate, roughness, and slope are substituted in. We drop the units and get 19.379. The area and hydraulic radius are rewritten in terms of the base width, b, and the water depth, d. To simplify, both sides of the equation are raised to the 3/2 power, and the equation becomes b times d to the 5/2 divided by the quantity b plus 2 times d equals 85.309. Next, the base width of 8 feet is substituted in for b. Now we're left with one equation and one unknown. If we had access to a calculator which can solve polynomial expressions for the roots, we would simply find those roots and determine which of those 5 roots equals one of the 4 possible solutions. But assuming we don't have access to that kind of calculator, another quick way to solve this problem is guess and check. Here we see the possible solutions for the water depth, d. If we graph the equation on the left, it takes the general form of depth to the 3/2 power equals flow rate. The purpose of this graph is to show that the relationship between the depth and the flow rate is 1-to-1 between the possible solutions for d. This means we should evaluate the left-hand side of the equation for d equals 2 or d equals 3 to minimize our chance of not knowing the solution after the first iteration. If we set d equal to 3, the left-hand side equals 201.6. This is greater than 85.309. Since q increases as d increases, the next d should be smaller than 3. Evaluating 1.5, the left-hand side equals 45.3. Now we know the depth should be 2 feet. The answer to this problem is B.